There's somebody in the lobby. Florencia, are you monitoring that?
Yes, sure. Everyone is now entering into the room.
Okay.
So let's start.
We are 2 minutes off.
Yes, so let's start. So good day or afternoon, everyone, and welcome to our webinar, Nuclear Weapons Pathways to Verify Disarmament. We're delighted to have you join us for this important discussion on one of the most pressing issues in global security today. Our goal in this session is to provide a clear understanding of how nuclear weapons operate, the international frameworks that govern their control, and the technical and diplomatic pathways toward verified disarmament. This conversation is crucial because achieving a world free of nuclear weapons requires not only political but also robust technical solutions and international cooperation. We have today an outstanding lineup of speakers: Peter Andersson, Associate Professor at Uppsala University, who will share insights on the fundamentals of nuclear weapons and technical verification methods, and Eva Giane, Technical Lead at Within Global, who will be guiding us through the role of NPT, IAEA safeguards, and the Treaty on the Prohibition of Nuclear Weapons. So today's session will cover 4 key topics: an introduction to nuclear weapons, the NPT and the IAEA safeguards, technical pathways for verified disarmament, and the role of the Treaty on the Prohibition of Nuclear Weapons. We encourage you to engage actively, share your questions in the chat, and we will address them during the Q&A segment. Together, let's explore how science, policy, and diplomacy can converge to make verified nuclear disarmament a reality. So let's begin with our welcome message. Please allow me to introduce Lancy Neto, Newcomers for Nuclear Global Coordinator. He has over 5 years of experience in nuclear energy, focusing on education, security, non-proliferation, and the climate and nuclear nexus. He recently led the first edition of Newcomers for Nuclear Summer School, a 2-week program featuring experts from IAEA, WINS, and the World Nuclear Association. As a negotiator for Burkina Faso at COP27 and COP28, he brings expertise in climate and scientific diplomacy. Lancina is the founder and president of Young Generation in Nuclear, a member of African Young Generation in Nuclear, and organizes weekly webinars to empower youth in nuclear advocacy. He also founded Women in Nuclear Burkina Faso and STEM initiatives, Academically, he holds a diploma in technology, a DESS in SME management, and pursuing masters in project management. His certifications include radio protection, nuclear disarmament, Gen 4 simulation, and Pan-African nuclear energy training. He actively contributes to global security through the African Research and Innovation Hub for nuclear disarmament verification. So, Lancine, please, over to you. Thank you.
Okay, thank you so much, Florencia. Good morning, afternoon, and of our evening, distinguished guests, colleagues, and participants. A very warm welcome to all of you joining us today from across the globe. I'm Lance Dato, Project Manager Coordinator of a working group, Newcomer for Nuclear Global, and I'm your host for this important webinar that end 2025 year. The topic we are gathering here to discuss nuclear weapon path to verify disarmament, or more broadly, the control of illicit arm flow and non-proliferation. It is a critical importance in our current global security landscape. We are living in a complex area marked by evolution of risk and rapid change in technology and destabilizing accumulation and determine international peace and security. The goal of this webinar is to provide a comprehensive overview of nuclear weapons and the international framework guiding their control and elimination. It begins with an introduction to the fundamental principle of nuclear weapon and fissile material, followed by an exploration of the Nuclear Non-Proliferation Treaty and the IAEA Comprehensive Safeguard Agreement. The session that exempted technical pathway for verifying nuclear disarmament and lighter similarities and difference with existing safeguard. Finally, the role of the treaty and the prohibition of nuclear weapons in shaping global disarmament effort will be discussed innovative. Over the next 1 hour, we will hear from leading experts in the field who will share their insight and expertise. We'll have an excellent link-up of speakers, and we are confident that the knowledge shared today will be invaluable to our collective effort. Before we begin, we would like to offer special thank you to our organizing team and our partner to this webinar, Sina Olbach from Uppsala University, for making this event possible. To our audience and strongly encourage active participation. Thank you for all being here and for commitment to this vital cause. Your presence is a testament to the shared desire to make a world a safe place. With fewer, Aldo, let's begin with our moderator to continue. Thank you.
Thank you very much, Lancina. Those were wonderful welcoming remarks, and please allow me to move on to the introduction of our both distinguished speakers for today's session. So let me start with Peter Andersson. He's an associate professor in the Division of Applied Nuclear Physics at the Uppsala University, where he leads a work group on technical verification and monitoring for the Alva Myrdal Center on Nuclear Disarmament. His research focuses on non-destructive assay of nuclear materials to look inside without opening, utilizing neutron and gamma ray techniques for applications in disarmament, verification, nuclear field performance, and nuclear safeguards. Peter has a PhD from Uppsala University specializing in fast neutron tomography using portable neutron generators. Following his doctoral studies, he served as a postdoctoral research at the Halden Reactor Project in Norway, pioneering massive gamma tomography for examination of used nuclear field. In 2023, he joined the International Partnership for Nuclear Disarmament Verification, IPNW, contributing to global efforts in advancing verification mechanism for arms control. We will have this exchange presentation between Peter and Mrs. Eva. So without, let me just introduce also part of the academic and professional experience of Eva Gianni. Eva Gianni is a senior nuclear professional with more than 40 years experience in the nuclear field at the international and national levels, having worked at the IAEA as a nuclear safeguards inspector and in other positions in the Department of Safeguards, as well as the United Arab Emirates Federal Authority for Nuclear Regulation as a senior nuclear export control specialist. At the IAEA, she was the senior inspector for implementation coordination in the Iran Task Force, overseeing the work of inspection teams during the preparation of the implementation of the Joint Comprehensive Plan of Action, JCPOA, well known. Mrs. Gianni is actively involved in Women in Nuclear Global, where she holds the position of technical leader and leads the group Win for Peace. She was the president of Win IAEA chapter from 2009 to 2016. Mrs. Gianni holds an MBA from the Economic University of Vienna, a bachelor's in science and physics and chemistry from the Open University, and a master's in science in nuclear science and technology from Manchester University. So please, Mrs. Eva and Peter, you can proceed and the floor is yours. Thank you for being with us.
So thank you. Should I start to share my screen and make my first presentation?
Yes, please, Peter. Over to you.
Thank you very much. Can you see my presentation slides now?
Yes, I confirm I can see those.
Perfect. Thank you very much for inviting me. It's an honor to come here to Newcomers for Nuclear and present. So we'll talk a lot about non-proliferation and disarmament verification later. In this first 15 minutes, I will present about an introduction to nuclear weapons. The purpose for this is to properly understand the basics of the principle of operation of nuclear weapons, and having that knowledge, it helps to see how the nuclear weapon problem has a definable boundary and can be put under international control, essentially. Firstly, I have this photo from a nuclear test. I'm sorry, it's a bit of a cliche to show a nuclear test explosion, but it serves as a reminder that nuclear weapons are enormously destructive. This is the Castle Bravo test, the test in the Pacific Ocean that had explosive yield corresponding to 15 million tons of conventional explosives of TNT. So of course, any such device used in a population center could cause millions of casualties, and it truly is weapons of mass destruction. And it can be understood easily that with such weapons in the capability of human civilization, we must show some kind of collective restraint. We cannot make and use all the worst weapons that we can, or that will mean the end of humanity. So that's the topic of today. And what I will start with is to try to help you understand how is it possible to make such destructive weapons. It can seem almost like some dark magic, but there is physics laws of the nature that lays the ground and enables this kind of weapons. So I'll try to explain some discoveries in physics made in the 20th century that enable these weapons, and that understanding will give some key conclusions about how to control nuclear weapons also. So this is a artistic rendering of the atom structure made by a PNNL artist that I like very much. It shows the understanding from about the 1920s of how the atom is built up, and you see that we have a positively charged nucleus in the center, and this is orbited by electrons that are attracted by their negative electric charge that is attracted by the positive charge of the nucleus. One great surprise discovered by Ernest Rutherford, a physicist, is that this nucleus in the center is very tiny. This image is not to scale. Actually, the nucleus is only about 1/10,000th of the size of the electron orbits. And this was a great surprise. So why was that a surprise? Well, the electrons are bound by the nucleus by their opposite charge. That was well understood at the time. But the nucleus consists of protons and neutrons, and protons are all positively charged. They should have a repulsive electric force. Why doesn't the nucleus just rip apart instantly, driven by this electric repulsion? And the only possible reason for this is that there must have been another force that is only visible in the very small range in the scale of the nucleus, which is on the femtometer scale, is very tiny, and that is very strong, so it overcomes this electric repulsion. So without much imagination, this was named the strong nuclear force. So that was a main enabler, one of a few in the 20th century that enabled nuclear weapons to be created. So early physicists, they investigated all the abundant elements in nature and looked at the nuclear binding energy of these, and they find that the scale of this nuclear energy is great. It is much more energy released in a nuclear reaction than in any chemical reaction, and is about 1,000,000 times larger in magnitude. So it's found that the lightest atoms have no nuclear binding energy. A simple hydrogen is just a proton, it's not bound to any other protons or neutrons, whereas the heavier atoms have more nuclear energy, and there's an optimum around iron 56, a medium heavy nuclide in nature. Beyond that, the nuclear attraction is somewhat compensated by the strong electric repulsion of all the protons in the nucleus. So there is like an optimum in nature, and if we can have a nuclear reaction that fuses lighter elements towards iron, or that can split up the heavier atoms towards the mass of iron, then we can release huge quantities of energy. At first, however, that seemed nearly impossible. Even the father of nuclear physics, Ernst Rutherford, he said in a famous speech in 1932 that anyone who's looking for useful energy from the transformation of nuclei is talking moonshine. And the reason for this is that it's very difficult to make nuclei react with each other. The range of the strong nuclear force is so tiny that if you try to make them collide, they will mostly deflect before coming close to each other because of this strong electric repulsion between like charge. However, Rutherford forgot about one recent discovery. That was the discovery of the free neutron. Free neutrons are the only type of nuclear matter that has no electric charge. It's neutral. So neutrons can easily get absorbed by any other nuclei in its environment, and is therefore a very good catalyzer of nuclear reactions. In the years that followed after the discovery of the neutron, physicists tried to bombard neutrons on basically any element in nature to study the nuclear reactions that it caused, and to try to make new artificial elements. And the most disruptive discovery took place in 1938, when Otto Hahn and Fritz Strassmann discovered induced nuclear fission. So they noticed that if they irradiate uranium, one of the heaviest element in nature, with a neutron, they sometimes get one of the isotopes in uranium-235, to absorb a neutron, and it starts a vibration that is uncontrolled, and it splits into two lighter nuclei. A large amount of energy is released in the process, but the most important thing with this reaction, that was a game changer, is that you have also a release of a few additional neutrons from the two fragments, the fission fragments that are created. So this as you see, is a reaction that is induced by a neutron, and it releases multiple neutrons as a result. So if you put a pile of the uranium isotope in that is relevant for this, uranium-235, you can have this reaction propagating as a chain reaction. If the pile is too small, most neutrons will leak out and it will die out. But if it's sufficiently large mass, a critical mass, it will be self-sustaining. And if you have more mass than that, it's supercritical, and it will exponentially increase in the rate of energy release. So in the case of uranium-235, that is abundant in nature, the critical mass is about 50 kilograms. Another important nuclide that has the same properties, that is fissile, it can sustain a nuclear chain reaction, is plutonium-239. It has a slightly smaller critical mass of about 10 kilograms. It depends also a little bit on density, purity, if there's something reflecting outside. So this is not precise quantities. It can depend on the situation a little bit. So this leads us to the principle of operation of a fission nuclear weapon. So you need to start with some configuration of a fissile material that is subcritical. It's not supporting a self-sustained nuclear chain reaction. For example, you can take a supercritical mass, but that is divided in two separate parts and kept at some distance. And you can, for example, shoot one at the other using a cannon-type assembly, where you have conventional explosives that is used to shoot one half to the other. When they combine, they form a supercritical mass, and in that case, it is impossible to stop the chain reaction from happening. In this case, it's not even only simple to achieve macroscopic energy release, but you can basically not hinder it. Another approach is the implosion-type assembly, where you have a subcritical pile that is compressed by having a spherical arrangement of high explosives around it. It's made to explode and compress with a shock wave the fissile material until it becomes of a supercritical state, and from that moment it will happen the same thing. Neutrons need to be injected at the optimal moment, and then every 10 nanoseconds you have a multiplication to a new generation of neutrons that is bigger than the previous. After about half a microsecond to 1 microsecond, the chain reaction will have culminated, and for every kilogram of the uranium or the plutonium that is fissioned, you have an energy release of additional 18,000 ton of conventional explosives, TNT, that is released. So these are fission weapons. Of course, many modern weapons are hydrogen weapons or thermonuclear weapons. In these, you use also some light elements, such as hydrogen, to fuse them and release additional nuclear energy. This is exactly the form of nuclear reaction that Rutherford thought of as impossible, because you need to overcome the Coulomb force, the repulsive force between like charge. What Rutherford didn't think about, of course, is that you could use a fission primary stage to heat, compress, and ignite a thermonuclear stage as a secondary stage of a nuclear weapon. So in this way, one can obtain a thermonuclear weapon. However, the key message that I have on this topic is any type of nuclear weapon, including thermonuclear weapons, will need to have the fissile material of the primary stage. So this helps to make the nuclear weapon problem to have a definable boundary. Without fissile material, you cannot make a nuclear weapon. So fissile material, how is it produced? There are essentially two paths to fissile materials. It's a uranium path and the plutonium path. So let's dig into both of them, starting with uranium. So natural uranium, it is an element that is abundant in nature. There are identified resources of about 7 million tons worldwide. So it's not very scarce. It's available in the crust almost everywhere. However, the vast majority is not a fissile isotope. It's uranium-238, which does not support a self-sustained chain reaction. There is only 0.7% of the abundant uranium that is the right isotope that is fissile. So natural uranium as it is not fissile. It needs to be isotopically enriched on the isotope that is fissile to about 90% to be suitable for nuclear weapons. Isotopic enrichment is a very technically involved process that is expensive and has a big footprint. The main technology that is used for isotopic enrichment today is gas centrifuges. So in a gas centrifuge, you have a drum that is spinning very rapidly, tens of thousands to 100,000 of revolutions per minute. And this is filled with a gas, uranium hexafluoride. And due to the centrifugal force, the heavier uranium-238 is concentrated at the periphery, and the lighter uranium-235 is somewhat more in the center. And then you have a clever arrangement of scoops that makes some an enriched stream of the lighter isotope pass a buffle and get scooped up separately. So you have a product stream that is just slightly enriched, and you have also a waste stream that is scooped up, which is just slightly depleted on uranium-235. So in order to get to the desired throughput and to the desired enrichment levels, one need to arrange large cascades where you have the product from one uranium centrifuge stage fed as input to the next stage, and so on. In essence, you need hundreds to thousands of centrifuge units to have a desired throughput and the desired enrichment of the final product. This process is very inefficient because in the end, there's only about 0.7% that is uranium-235 in the feed, so the product cannot be larger than that, essentially. And it also has a large footprint. It requires a lot of energy and, of course, finances and technological know-how. So in principle, there are many ways one can detect such activities hypothetically. Plutonium is the other major fissile nuclide, and plutonium is created by neutron absorption in the majority isotope of uranium, uranium-238. This produces uranium-239, which beta decays twice, and then you have plutonium-239 that is a fissile nuclide. And the most practical way to obtain plutonium is to irradiate uranium in a nuclear reactor. This is an example of a plutonium-producing nuclear reactor from the 1940s in the US. Typically, such plutonium-producing reactors have a moderator, which is meant to slow down neutrons and make them more reactive, so you can use natural uranium that is not enriched as a fuel in the reactor core. And the moderator choices then that one have is to use either graphite or heavy water. Fuel is inserted and must remain for only a short time in the core. In the end, about 1 per mil of the original uranium is converted to plutonium, and the fuel that is extracted from the core needs to be reprocessed chemically to separate that plutonium. So it's also a very inefficient process, and it has also a detectable footprint. There are some releases of radionuclides typically. There's a production of heat as well as radioactive waste products in the fuel itself. So it's a technically involved process, just as uranium enrichment, and it has a detectable footprint. So that's the first part of my presentation on the introduction to nuclear weapons. So the key takeaways that I will leave you with is that all nuclear weapons require fissile material to function. And the main options for that is highly enriched uranium, enriched on uranium-235, or plutonium produced in reactors. So achieving these materials require specialized and advanced production facilities, either enrichment facilities or reactors and reprocessing. And in addition to this, all fissile materials are radioactive. That means that they emit radiations that can be helpful to use non-destructive assay to assess them. And a common misunderstanding is, of course, that all radioactive materials can be used to make a nuclear weapon. That's not the case. Fissile materials are required, and they are only a very small subset of radioactive materials. And finally, the production facilities of fissile materials, they are large and expensive and complicated, and they have a multifaceted footprint. So it helps in order to make a verification system where you need to be reliably able to detect such facilities for the verification purposes. So with that, I end the first part of this presentation. Later we'll talk about disarmament verification, and first we'll have a section on non-proliferation and the IAEA. I don't know if I have time for questions, but maybe we can take that now or later. I will leave to Florencia to decide that. Thank you.
Thank you, Peter. Thank you for this wonderful introductory session in this first presentation. If it's okay for the two of you, we can assign to the Q&A session after both of you have concluded your presentations. We don't see other additional comments in the chat, but we invite all the attendees to share your thoughts and comments in the chat or the Q&A section as well. Thank you, Peter. Now we would like to continue with Mrs. Eva's presentation. Mrs. Eva, the floor is yours.
So hello also from my side, and thank you very much to the organizers for inviting me for my talk as well. So thank you, Peter, for giving us the basics of how nuclear weapons work. And what I'm going to do now is to give you some historical overview what happened after the fission process was discovered. Can you just confirm that you can see my presentation in presentation mode?
Yes, now it's perfect.
Okay, thank you. So I will give you this brief historical perspective and then tell you more about the IAEA and the Non-Proliferation Treaty, about IAEA safeguards and their implementation, and about what the NPT has accomplished and what are its failures. I was in Hiroshima and Nagasaki this summer, 80 years after the two explosions happened. So when fission was discovered, there was also the potential mentioned for energy production, but unfortunately, the fission process is dual use. It can be used both for peaceful purposes and for military purposes. And unfortunately, the first use was for military purposes, where the US dropped nuclear weapons on Hiroshima and Nagasaki, which led to horrible destruction. And if ever you are in Japan, I encourage you that you visit these two cities just to appreciate what a nuclear weapon, the very first of its kind, could do. So in 1945, we had one nuclear weapon state, the USA. Shortly after, some others followed. But until 1953, the nuclear chain reaction and the theory was a very secret theory which was kept under only for a few states. And it's only in 1953 that Dwight D. Eisenhower, the US president at that time, decided to open the nuclear theory for peaceful uses by launching the program Atoms for Peace, where all countries should have access to nuclear technology, and there should be an agency that should oversee the use of nuclear energy, which would, and that agency should be based under the United Nations. This led to the creation of the IAEA in 1957. So this is an old photo of the IAEA headquarters in Vienna, in the center of Vienna, many years ago, and 40 years ago they moved outside the center. The IAEA has basically two a little bit opposing missions. On the one hand, the IAEA promotes the peaceful uses of nuclear energy. On the other hand, it also controls the state's nuclear programs and ensures that these programs are used in a peaceful manner. Usually, you don't combine these two missions under one agency, but that's how the IAEA was set up. What happened later? So by 1964, there were already four more nuclear weapon states, namely the Soviet Union, the United Kingdom, France, and China. And by the late 1960s, about 20 more states were interested in acquiring nuclear weapons. So it became clear that this technology needed to be controlled. So this led to the drafting of the Treaty on the Non-Proliferation of Nuclear Weapons, for short NPT, which was opened for signature in 1968 and then entered into force in 1970. Let's look at the main provisions of the NPT. It has three pillars: non-proliferation, peaceful uses, and disarmament. So under Article 1 and 2, nuclear weapon states to the NPT commit not to transfer nuclear weapons to non-nuclear weapon states, and whereas non-nuclear weapon states commit to not acquire or manufacture nuclear weapons. Article 3.1 foresees that non-nuclear weapon states accept IAEA safeguards on all source and special fissionable material on their territory. Article 3.2 mentions nuclear export controls, so no state should provide source or special fissionable material or equipment or material especially designed or prepared to any non-nuclear weapon state unless that material is subject to IAEA safeguards. Then the second pillar is the peaceful uses, so that's the inalienable right of all parties to use nuclear energy for peaceful purposes only. And Article 6 says that nuclear weapon states should pursue negotiations in good faith on effective measures relating to the cessation of the nuclear arms race at an early date. As you can see, there's not really anybody in charge of monitoring this disarmament aspect, and the formulation of the text is really not very concrete, without any concrete date given. So under the NPT, we have 5 recognized nuclear weapon states: the US, the Soviet Union at that time, the UK, France, and China. And all other states can only accede to the NPT as non-nuclear weapon states. There are 4 states outside the NPT which have developed nuclear weapons. Israel, the exact date of their nuclear weapons program when it commenced is not known, but it was around the 1960s. India tested its first they tested a device for a so-called peaceful nuclear explosion in 1974, using material from a heavy water reactor that had been delivered to them by Canada. And in 1998, they detonated the nuclear weapon, and Pakistan followed suit just a few days later. And we also have the DPRK. Actually, the DPRK did accede to the NPT in 1985, but it withdrew in 2003. This was followed by a first nuclear weapons test in 2006, and now the DPRK, North Korea, is estimated to have about 30 to 50 nuclear weapons, and also the delivery systems which pose a threat to its neighbors and beyond. So let's look at some of these obligations by non-nuclear weapon states. So non-nuclear weapon states need to place all nuclear material and nuclear facilities under IAEA safeguards. They also need to allow the IAEA to independently verify the state's legal commitment not to divert nuclear material from peaceful uses to nuclear weapons. And this is achieved by the implementation of IAEA safeguards measures. First of all, let's look at Article 3.1, where states have to accept safeguards on all sources of special fissionable material. So which material is subject to IAEA safeguards? Source material is considered as uranium, natural or depleted, and thorium, whereas special fissionable material is what Peter was talking about, plutonium-239, uranium-233, and uranium enriched in the isotopes 235 and 233. As Peter has also mentioned that any other radioactive material is not subject to IAEA safeguards. It's radioactive, but only nuclear material is subject to IAEA safeguards. So nuclear material is uranium, plutonium, or thorium, and any other radioactive material is not subject to IAEA safeguards, but it still needs monitoring and control both at the national and at the international level. Under Article 3.4, states need to conclude a comprehensive safeguards agreement with the IAEA. And on the right-hand side, you can see this model agreement, which is based on INFCIRC 153. And this is concluded between the IAEA and the respective state. And this document contains the main provisions for the application of IAEA safeguards. So what are IAEA safeguards? IAEA safeguards, one can say, are a set of technical measures that are applied on nuclear material and nuclear activities by the IAEA, whereby the IAEA seeks to verify that there is no misuse of nuclear technology or diversion of nuclear material from peaceful uses. Of course, states have some obligations as well. They have to establish a so-called SSAC, state system of accounting for and control of nuclear material. They need to provide certain information to the IAEA. They need to facilitate access by IAEA inspectors, and they need to cooperate with the agency. And the objective of IAEA safeguards is the timely detection of the diversion of significant quantities of nuclear material, either to manufacture nuclear weapons or other nuclear explosive devices, or for purposes unknown. And these serve as a deterrent of diversion by the risk of early detection. So what are some of the limitations of IAEA safeguards under a comprehensive safeguards agreement? First of all, this agreement assumes that all states provide accurate and honest declarations, and there's a huge focus on the declarations, on anything that is declared and whether that is really correct. The frequency and location of the access are a little bit limited and routine. And the CSA doesn't provide the tools to detect the absence of undeclared nuclear material and to detect any undeclared nuclear material of facilities. So this completeness aspect is lacking from the CSA. That is why the IAEA had an eye-opening experience in 1991 in the case of Iraq, where there was a huge nuclear site at Tuwaitha with different buildings and 3 declared facilities to which the IAEA had access. That's the 3 buildings in green. But the other buildings in red show the other buildings where certain activities were going on related to enrichment, reprocessing, and weaponization, which had not been declared to the IAEA. So this came to the light during the first Gulf War in 1991. And this led to a rethinking and an eye-opening for the IAEA, which realized that it needed to strengthen this comprehensive safeguards agreement framework by introducing the so-called additional protocol to the safeguards agreement. On the right-hand side, you will also see the model based on INFCIRC 540. And in principle, these provisions of the additional protocol provide the IAEA with enhanced access, and also states need to provide more extensive information. And the main objective of this agreement is to give the IAEA the tools to detect also undeclared activities and to get a more complete picture of states' nuclear programs. So this agreement or this additional protocol to the agreement provides a tool to also verify the completeness of state declarations. Now let's look at how safeguards are implemented. So you will have heard about IAEA inspections and inspectors. The principle is that once the state concludes a comprehensive safeguards agreement, they need to put all nuclear material and all nuclear facilities on the territory under IAEA monitoring. That means they first of all provide a declaration to what facilities exist and how much material there is. And they do so by an initial inventory declaration. And whenever there's a change to the inventory, they also have to provide nuclear material accounting reports to the IAEA. Then IAEA inspectors come and verify the correctness of those declarations and also verify the activities that are going on at the respective facility. So the objective of inspections is to detect the diversion of declared nuclear material for prescribed purposes, and with emphasis on declared. How does this happen in practice? So the inspectors get to the facility, and first of all, it's the most important initial activity is to do a book audit and to examine the facility records to ensure that they are all consistent with the state reports that are sent to the IAEA. And this also serves to establish a sampling plan for the verification of the items. The IAEA seldom verifies 100% of the inventory. That is just not possible, especially for large facilities. So it establishes a sampling plan depending on the on the amount of nuclear material present and on the type of nuclear material present at the facility. So the more nuclear material and the higher, for example, the enrichment, the more inspections there will be and more items will be verified, whereas if there is just some small activities, the verification measures will not be very often. One activity is item counting and tag check. So here you see a large amount of UF6 cylinders. Each of them has a so-called tag. So the IAEA inspectors get the declaration from the facility operator. They count the items and randomly check the tags on the items, whether they correspond with the list that they have been provided. Sometimes nuclear material items are also weighed, as you can see here. And another measure is so-called containment and surveillance. So the IAEA uses seals to contain nuclear material items to maintain the so-called continuity of knowledge. And here you see different types of seals. So this is on the left-hand side is the old metal seal that is now being replaced by the seal on the right-hand side. And there are also electronic seals, as you can see at the bottom. Surveillance is achieved either by inspectors or by cameras, usually by cameras only. So cameras are installed in certain strategic locations at facilities where they capture images of what is going on at the facility at certain intervals. And these surveillance records are then reviewed by IAEA inspectors, and they detect whether there are any activities that where nuclear material could have been taken out of the facility, for example. And here you can see some photos of these cameras and the IAEA inspector, the IAEA Director General with one of them. Inspectors also conduct non-destructive assay NDA measurements using different equipment, for example, mainly gamma detectors and neutron detectors. So these are independent measurements to verify the declared quantities and isotopics of nuclear material. There's another device, which is a very new device, which is being introduced by the IAEA, the robotized Cherenkov viewing device for spent fuel verification, where the device detects the Cherenkov glow coming out from the spent fuel. So this is a very new device, as I have said, which is not yet fully deployed, but just to give you an idea, when there's spent fuel in storage, that's also verified by the IAEA, and this is one of the methods. The IAEA also takes nuclear material samples for destructive analysis, not in situ, but those are sent to the IAEA laboratories. So on the left hand, you see little plastic bottles for probably UO2 powder. And on the right-hand side are the UF6 sampling devices. Another important verification measure is so-called environmental sampling, which was introduced in the 1990s when the additional protocol was established. And this is a very powerful tool which enables the IAEA to detect, based on what is seen on those samples, any past and current nuclear activities. So on the left-hand side, you see the sampling kit. You see the cotton pads on the right, bottom right of that left picture. In the middle, you see the sampling of certain process equipment. So when you take samples, you really have to think where is the best place to take those samples, where you can expect some signatures. And those samples are then analyzed both at the IAEA and at the network of analytical laboratories. So and they are anonymized, so nobody knows where they come from or what they are, and they are analyzed by at least 2 or 3 laboratories. So let's now look at the NPT accomplishments. The NPT was indefinitely extended in 1995, and there is an NPT review conference every 5 years. The next one is scheduled to take place next year. And one can say that the NPT is the most adhered to treaty in the world, and it's considered to be the cornerstone of the global non-proliferation regime. After how many years? 45 years of NPT, there are just 4 states outside the NPT with nuclear weapons. So the NPT has been quite efficient in containing the acquisition of nuclear weapons by other states. And all non-nuclear weapon states are under excellent IAEA monitoring. Let's look at also some of the failures. As I have said, the text of Article 6 is very fluffy, and there are no concrete dates for nuclear disarmament. So also there is no IAEA equivalent, no entity that is responsible for supervising the implementation of Article 6. As a result, there hasn't been any progress on disarmament, so there have been reductions of nuclear weapons by the 2 big states, Russia and the US, but there has not been any disarmament yet. Currently, we have about 12,000 nuclear warheads with stockpiles growing. Instead of disarming, nuclear weapon states are refurbishing their nuclear arsenals, and we currently have a geopolitical situation where some non-nuclear weapon states are actually considering to acquire nuclear weapons, or at least to be under a nuclear umbrella by one of the nuclear weapon states. So in my opinion, we are going in the wrong direction, and let's see what the future will bring. So that brings me to the end of my first presentation. And I'm looking forward to your questions later when the time comes. Thank you.
Thank you so much, Mrs. Eva, for this wonderful section of the program. We really appreciate all the information that you're sharing and from your experience and all the cases that you have completed and supported in the past years to the agency while you worked there. We really appreciate that. Now we would like to continue with Peter's presentation for this second section of the program. So please, Peter, over to you. Thank you.
Thank you very much. So that was very interesting to hear about the verification of the Non-Proliferation Treaty. Thank you, Eva. And now I'll continue looking at expanding the verification to a framework that also includes disarmament of the existing nuclear stockpile. So before starting, maybe we should define what are we going to talk about when we mean, what do we mean when we talk about disarmament? There are many different definitions of disarmament. The eponym of our center, the Alva Myrdal Center, Alva Myrdal, she used a very broad connotation of the word disarmament that included everything from non-proliferation to nuclear test bans and no first-use pledges and export control, etc. But what I will talk about now is more limited. I will talk about verification of a comprehensive nuclear disarmament, something in accordance with Article 6 of the NPT, a treaty on general and complete disarmament under strict and effective international control. So strict and effective international control here would mean verification. So removing all nuclear weapons, essentially. Sorry. So what is verification then? Let's also try to define that. There are many definitions of verification that are circling around. Usually it's on the topic of demonstration of compliance or objective assurances that commitments are being honored. I try to find one authoritative source. Maybe the IPNW can be used, the International Partnership on Nuclear Disarmament Verification, as defined verification in the following way. Is the iterative and deliberative processes of gathering, analyzing, and assessing information to enable a determination of whether a state party is in compliance with the provisions of an international treaty or agreement. So, as you can see, a physicist like myself like a short definition, where I think that diplomats and lawyers have been involved in adding a few words in the IPNW definition. But there are various definitions, but they're all in the same region, I think. So is it necessary to have verification? One may ask. It could be criticized that it's difficult to negotiate the verification and could hinder a treaty to be signed. There are historical examples of disarmament treaties that have been lacking any provisions for verification. One notable example is the Geneva Protocol from 1925 that prohibited the use in war of asphyxiating, poisonous or other gases and also bacteriological methods of warfare. So how come they could agree on a ban of use of such weapons without verification? Maybe a reason for that is the limited scope of this ban. The use in war was in this case prohibited, but the production of the said weapons, the stockpiling of the weapons was not banned. And in fact, some of the signing nations also made a declaration that they will respond in kind if ever attacked by these weapons. So in such a limited disarmament, maybe verification is not needed. But one can assume that the deeper reductions that are mandated by a treaty, the stronger the corresponding demand for robust verification is likely to be. So what are then the benefits of verification? The first objective is to build trust between the member states to a treaty that the commitments are being honored. So it's a trust-building exercise mainly. But it needs to build that trust through deterring from non-compliance, and it deters from non-compliance by being able to detect it. So if it is not able to detect non-compliance, well, then it will not deter from it, and then neither will it build any trust, of course. Then the whole verification framework falls like a domino. So for effective verification, you need to be able to detect any plausible non-compliant behavior from the member states. And this is, of course, essential not only after the treaty comes into effect, but already in the negotiation of the treaty. It may be very valuable to build that trust, that commitments that are being made will be honored. So, looking at the anatomy of a verified nuclear treaty, one can in general say that something is subject to accountancy in the treaty. There may be items that are countable or materials that you have an amount of. You need to make declarations how much you have, how you're using it. So some facilities where this is present will also be required to be declared by the states, and notifications need to be sent when any relevant action is being performed on the treaty countable item or material. So verification encompasses two things and two things only, as Eva already said, is correctness and its completeness. So any declarations or notifications that is sent by the member state, are they accurate? That's correctness verification. And furthermore, are they complete, or is anything left out that should be in the declarations? That's completeness verification. So in the case then of comprehensive nuclear disarmament, what can be agreed and verified? There are two main approaches in nuclear disarmament verification. Either use a fissile material approach. The reason for that, I hope, is clear after my first presentation. Without fissile material, you cannot produce any nuclear weapon. And this is, of course, the strategy that is used, for example, in the NPT, even though in the NPT, as you heard, all nuclear material is covered by the verification, not only the fissile material, but also the source material, such as natural uranium and thorium, that can be used to produce the fissile material. So it's expanded the scope slightly. Also, I will talk more about the fissile material cutoff treaty. That is a proposed future treaty that could be expanded to include also the nuclear weapon states. Another approach is the nuclear warhead approach, where you have items of nuclear warheads that are the item under accountancy. This has some distinct advantages. Nuclear warheads is presumably well known to the host, to the member state, exactly how many they have, and you can verify the authenticity of each of them, and you can dismantle one by one and count one off every time you do so, and eventually you have zero left. So fissile material, on the contrary, there is some uncertainties about the exact amount of materials, so countable items has some advantages, so we'll come back to that. Starting with the fissile material cutoff treaty, sometimes also called the fissile material treaty or fissile material control treaty. The main idea here is to ban the production of new fissile material for use in nuclear weapons. And that would then affect the nuclear weapon states. Such a treaty would not affect the non-nuclear weapon states that are signatory to the NPT, because they are already under the IAEA safeguards, so they would not be required to change anything. On the other hand, any non-signatory states that are de facto nuclear weapon states, such as Pakistan, India, Israel, DPRK, for example, they could also be entering a verified framework if entering the FMT or FMCT. So, because this has large similarities to the IAEA safeguards, the verification could largely mirror the IAEA safeguards that are already developed and in place since the 1970s. There are, however, some differences that are notable. And one important thing is there is an unsolved question whether if stockpiles of fissile materials that have been previously produced should be included in the scope of the treaty. Of course, in order to get comprehensive nuclear disarmament, you need to include all the historically produced material. Otherwise, you just freeze the amount of fissile material at current level, but you wouldn't reduce the amount of fissile material available to nuclear weapons. So it could make the treaty much stronger, but it also brings challenges for the verification. As you see in this table, that is a table of highly enriched uranium available in different nuclear weapon states, as well as plutonium. is put together by the International Panel for Fissile Material. You see that the total stockpile amount is more than 1,000 tons of highly enriched uranium and many hundreds of tons of plutonium. And this is a notable amount because if you compare with the significant quantity used by the IAEA, that's 25 kilograms of highly enriched uranium or 8 kilograms of plutonium. So if you would verify existing stockpiles and let's say you have an uncertainty in the end of 1%, for example, that is still thousands of significant quantities. So it's difficult to achieve high precision in any verification system for existing stockpiles to ensure that declared stockpiles are complete. The means that is available for verifying stockpiles is called nuclear archaeology. So the principle of nuclear archaeology is that you try to find operational records of the historical production. So historical production could in some countries have taken place so early as in the 1940s. So operational records may be incomplete or flawed in many ways. Staff that is involved is dead by now. So it's of course difficult to know precisely what kind of operations they did in their enrichment facilities, in their plutonium production reactors, etc. There are several training and test projects where nuclear archaeology is tried as research. This is an example from a Swedish project where we are trying to explore nuclear archaeology methods on the plutonium production in the Ågesta reactor that was operated in Sweden partially before we entered the NPT. And one can obtain, for example, as you see, core maps of fuel loaded into the reactor in different core loads. You can obtain dimensions and design of the fuel elements, and you can also obtain power histories of the individual fuel assemblies that were used in the reactor. And using this kind of data, a verification body or a researcher in our case could obtain a model for the plutonium production and estimate the plutonium inventory that should have been produced historically. And this can be checked with a declared plutonium inventory by the state in case we have an FMCT, in order to see if there is a consistency between the calculated plutonium inventory and the declared plutonium inventory. Of course, this has some downsides. It's based on comparing a declared plutonium inventory with a declared operational history. This is provided by the host state, after all. On the other hand, one can go towards more independent verification by also including measurements of structural material that was used in the reactor in this case, where the neutron flux that caused the conversion of uranium to plutonium also has exposed all the structural material in the core and changed the isotopic abundances in the structural materials, such as the moderator and other components in the core. So by accessing and measuring the isotopics of these materials, one can obtain an independent verification also that is not totally dependent on the declared operational history given to you by the nuclear weapon state. In the end, it is difficult to imagine that there will be percent level precision of any verified stockpile. It means that it's an effective way to start off a disarmament that is verified, but at the end there will be a significant uncertainty, and there may be unaccounted for material that one have to accept with a fissile material approach. So therefore I will go into the other approach, that is a nuclear weapon dismantlement approach, or a warhead dismantlement approach, that has gained a lot of interest, especially in the last decades. So in this case, you have nuclear warheads that are the subject of the accountancy, and you can dismantle them until you reach an agreed limit of number of warheads, or in the end you can lower that limit until you have a complete elimination of all nuclear weapons. As always, verification will entail correctness of declarations, the numbers and locations of warheads, as well as the completeness to make sure that there's no hidden nuclear warheads or facilities that can produce them. So challenges and solutions in such a verification framework is being investigated by the International Panel on Nuclear Disarmament Verification, the IPNW, and they have set up a 14-step model to understand the disarmament life cycle of nuclear warheads, where you will start at the deployment site of nuclear weapons. This is the first place where inspectors could encounter the nuclear warheads. In this location, you would typically unmate a warhead from a delivery system, and it will be containerized and stored. And then you have a process in 14 steps that are envisaged here, where you have transports and temporary storages until you reach a disassembly site, that is the middle row here. And the crucial step here is the facility in the middle, step 8, where you dismantle the nuclear warhead. And that is operationalized as separating the fissile material from the high explosives that are used to insert the reactivity. So after step 8, you have no longer any warheads, you have high explosives components, and you have fissile components that are transported through the life cycle until in the end you have disposition in the last step 14, where you safely dispose of the fissile material and the high explosives. So this framework needs to be verified, and there are a number of key processes that are envisaged to be the building blocks of such a verification. Firstly, we have absence measurements. So if we imagine that inspectors of a multilateral verification body comes to a storage, there should be a declaration stating the number of warheads there, so the host state can show the declared warheads containerized. And the role of the verification body will be partly to simply count the numbers and see that it agrees. But then you have possibly additional containers there that should not contain any nuclear warhead. So the role of absence measurements is to verify that anything at this location that is not declared as a warhead doesn't contain one. So this is relatively non-intrusive, because when you measure on something with radiation detectors, for example, it's not supposed to be a nuclear warhead inside. In that sense, you may use quite intrusive techniques, and it should not reveal too much information. Of course, you never see the actual warheads in such a verification regime that it's only reliant on absence measurements. However, as the progression of the disarmament continues, there should in the end be fewer and fewer declared warheads at the site. By not having anyone left, you can gain assurance that the disarmament is really taking place. However, further reinforcement of the assurance can be given if you also use presence measurements, or so-called authentication of the nuclear weapons. So in this case, you want to confirm that what is declared as a nuclear warhead actually truly is that. And here we could benefit from all the types of radiation measurements that are already used in safeguards by the IAEA, in order to confirm that fissile material is present, high explosives are present, and if they are both present, we can assume that this is a nuclear warhead. However, the big challenge in this case is that nuclear warheads are highly sensitive, so it becomes a trade-off between intrusiveness and, on the other hand, reaching the verification objectives. The nuclear weapon states have obligations in the form of nuclear safety. You may not do something that is dangerous. Nuclear weapons have high explosives. It has high amount of fissile material. You don't want to do anything that risks the safety of the personnel and the items. Secondly, you don't want to give national security sensitive information that can be used by an adversary of the nuclear weapon state to, for example, take advantage of the information gain. And you don't also want to release any safeguard sensitive information. The multilateral verification body may also contain personnel that come from non-nuclear weapon states, so they must not come from the exercise with knowledge gained on how to make good nuclear weapons. So performing presence measurements where you authenticate the nuclear warhead is connected to careful trade-offs between intrusiveness and the objective of the verification. Finally, we have also chain of custody that is that would be exercised in all of the steps, ensuring that any item that we have encountered in any of these 14 steps, if we counter the same item later, we know it's the same. So you would have containers equipped with seals, unique identifiers and tags, so we can recognize it. And you will also utilize all the tools that we heard about from IAEA in form of containment and surveillance, like perimeter portal monitoring, like video feeds, for example, on storages, to make sure that nothing has been diverted meanwhile the inspectors were not present. And together these different key processes can reinforce the assurance that the commitments in the Disarmament Treaty are being honored. So I will say something on the dilemma of measurements. I think I already mentioned that there is a sensitive trade-off here because there's safeguards relevant information, there's security relevant information that must not leak out to the inspector body's personnel. And of course, anytime you do a measurement, you reveal some information. You want to reveal the information needed to verify the declarations, but nothing else. So if you, for example, measure a gamma ray spectrum with a spectrometry system, you can sometimes obtain a rich flora of information that will exceed what you need to verify the treaty. So information barriers are one way to reduce the risk of giving too much information. You can, for example, make the detector not provide the full information. It shall only register parts of the spectrum, for example, that are relevant for treaty verification, and much of the spectra would be, in that case, censored already, not even stored on the equipment. Ideally, you have a traffic light output so that all analysis is done by a pre-programmed analysis framework that is like hiding any sensitive information from the inspector body and only shows a green light or a red light, depending on if the item that was measured was as declared or if it was not, if it's not as declared. So there are information barriers are one way to mitigate this kind of difficult trade-off between intrusiveness and the verification objective. Of course, it brings its own challenges. Who's going to make the instrument that is used? The verification body want to make sure that it's certified and does what it's supposed to, while the host state will want to do a good authentication to see that it's not doing something it's not supposed to do. So who lays the last hand on the equipment, and how do we assure its correct function? There are challenges here, naturally. Another issue that requires work is, as I call it, proving the unprovable. The completeness verification, just as in the IAEA verification work, also in a nuclear warhead dismantlement approach, completeness verification will remain a difficult challenge because once the nuclear warhead has been produced, it has a quite small footprint. It's not easy to detect with satellite monitoring, not necessarily with environmental monitoring, etc. So ensuring that the declarations are complete is a particular challenge. And it's very important, therefore, that all the relevant sites of the nuclear weapon enterprise is within the scope of the verified declaration. So there are no hidden corners in the state where the inspectors may never go, but they would be suitable to hide some nuclear weapons. It's also important that the verification body must be empowered to act on suspicions. So there must not be any safe corner anywhere in the state, essentially. And there is an important precedent here in the form of the chemical conventions, the Chemical Weapons Convention, agreed in the 90s, where you have essentially a possibility to do a challenge inspection at any part of the member state's territory if there are evidence found by the treaty organization or provided by national technical means of one of the member states, showing evidence that there seems to be a hidden chemical weapons program in a state. And then the verification body has the mandate to go there and make a challenge inspection. And this is very important in order to build this trust, because if there's a place in the state where non-compliance cannot be detected, well, then you have the domino effect. Then it doesn't deter from cheating, and then also it doesn't build trust that commitments are being honored. So with that, I end my presentation. Just to summarize, there are various approaches to verified comprehensive disarmament. The most important approaches would be a fissile material approach, and also the nuclear warhead dismantlement approach, where you benefit from having countable items that you can discount one by one when you dismantle them. To demonstrate compliance, verification must, as always, ensure correctness of declarations as well as completeness of declarations, where completeness often is the more challenging one. And clearly another issue to work on is the trade-off between low intrusiveness on one hand and managing with a verification objective on the other hand. So the path forward must be to develop a versatile toolbox so that the verification body can agree with a host state on a set of technologies to assess the declared nuclear weapons that are a good compromise between these two objectives. So that's it for me. Thank you very much for listening, and over to you again.
Thank you very much, Peter. That was a very, very great presentation in terms of the generic comprehensive of disarmament verification pathways, and we have learned a lot this time from you, so we really appreciate having you in the house. So now we will be ending with Mrs. Eva's presentation before we continue with the Q&A session. So Mrs. Eva, please, if you can conclude the part of the role of the Treaty of
thank you very much,
Florencia.
Thank you also, Peter, for summarizing how we could get to nuclear disarmament and also the challenges, because it's really going to be a lot of challenges. Who may see what, who may do what, and most importantly, there has to be some trust and verification. So still a lot of work ahead of us, and actually I don't see this happening anytime soon, especially under the current geopolitical situation. Anyway, what I want to tell you about at the end of this webinar is about a relatively new treaty, the Treaty on the Prohibition of Nuclear Weapons, which tries to address exactly this disarmament aspect of nuclear disarmament. So the TPNW, how it's called, it followed this history of the continued lack of progress of disarmament, and also there were growing international concerns over the humanitarian consequences of a nuclear war. And in the 2010s, the efforts to ban nuclear weapons intensified, and eventually this led to the negotiation and the adoption of the treaty in 2017 and its entry into force in January 2021. Currently, there are 95 signatories and 73 state parties. So you can see the map here. The red ones are the signatories, which still need to ratify the treaty, and the state parties are all those countries in blue. And as you can see from this map, it's basically the global south that has, who are the parties of the TPNW. There's no single nuclear weapon state or any state in Europe except for Ireland and Austria. So you can see there are a lot of challenges related to the TPNW. Let's now look at the main provisions of this treaty. It cites the prohibited activities like the development, testing, production, acquisition, and stockpiling of nuclear weapons. It prohibits their use or the threat of the use of nuclear weapons. It asks for assistance to victims to support all those who have been affected either by nuclear weapons use or by nuclear weapons testing. It also asks for nuclear cooperation for the peaceful uses of nuclear energy. And there is no dedicated verification verification mechanism. The treaty expects that states are transparent when they sign up to the TPNW. What is the impact of the TPNW to the non-proliferation regime? As I've said, the nuclear weapon states are not in favor of this treaty because they see it as a competition to the NPT. But the Global South considers this as a significant milestone for nuclear disarmament and sees it as a reinforcement to the NPT, in particular to Article 6 of the NPT on nuclear disarmament. And it also represents ongoing efforts to eliminate nuclear threats. I had the honor and pleasure to attend the third meeting of parties of the TPNW that took place in New York last March. That was 80 years after the first use of nuclear weapons in Japan. And there was a continued commitment to disarmament and to the elimination of all nuclear weapons during that conference. The conference also highlighted the humanitarian consequences, and it recognized the impacts on the people of Hiroshima and Nagasaki and on other victims of, especially of nuclear testing. The conference also emphasized the moral obligation and the need for awareness and prevention, because I think nuclear weapons and their impact are somehow being forgotten by society. 30 years ago, during the Cold War, this was omnipresent and people were actually training for what happens if there's a nuclear war. But nowadays, I don't see any demonstrations against nuclear weapons or against countries making threats of the use of nuclear weapons. There's also a gender aspect of the TPNW. There is a provision in the treaty on gender, taking all genders into consideration. And during the conference, this aspect was reaffirmed to seek gender equality in all disarmament efforts and to ensure that women participate in a full and equal and meaningful manner in achieving a world free of nuclear weapons. The meeting also asked for global action in view of the heightened geopolitical tensions and the risks of nuclear proliferation. So the TPNW has become a beacon of hope in these turbulent times. There are also efforts to universalize the treaty and for all states to sign and ratify the treaty. There should be a collective commitment to the complete, verifiable and irreversible elimination of nuclear weapons. So one can say that the TPNW is a crucial network for global disarmament and gender-inclusive efforts that also addresses nuclear threats So there were concerns raised about the remaining nuclear stockpiles, the refurbishment of current nuclear weapons programs, and the urgency for continued negotiations. There should also not be any nuclear threats, and it's important to maintain nuclear non-proliferation efforts. And one big event during the conference was the commitment to nuclear victims and future works. So there was an acknowledgement of nuclear victims, not only of the actual detonation in a war, but also of the detonations for so-called nuclear testing, which were nothing more than nuclear explosions, but not during war, but for testing purposes. It was also decided to create a trust fund for victim assistance and to call for humanitarian assistance and environmental remediation of all those territories that have been polluted through nuclear weapons testing. My personal experiences, let me share them with you. After having worked for so long in the nuclear field, I still learned a lot of new things during that conference. I didn't realize that there were actually 2,600 nuclear explosions between 1945 and the early 1990s until the Comprehensive Test Ban Treaty was negotiated. So can you imagine 2,600 explosions, nuclear explosions around the world, mostly without asking for permission by those who inhabited those territories and causing a lot of harm to the inhabitants and actually to all of us because of the fallout, etc., which was in the atmosphere. So those communities that were directly affected have not been taken care of by all those who conducted the explosions, those 5 declared nuclear weapon states. And during the conference, I listened to representatives from different communities that had been affected by nuclear test explosions. For example, I met a man from Semipalatinsk in Kazakhstan who had been born without arms, and he was actually the only surviving child of his parents. All his siblings had died because of the radiation impact on the next generation. There was also the speech, a very touching speech by the son of a British soldier who talked about how his father had been forced to witness nuclear testing over Christmas Islands and to watch that test explosion. And his father and also his siblings later died from the radiation-related illnesses. So with global tensions rising, we see again a world where nuclear deterrence is being framed as a viable defense strategy, which in my opinion, we should have moved beyond this a long time ago. We should bear in mind that a nuclear weapon or even a nuclear war does not know any national borders, and it would affect parties that are not involved in the conflict and eventually all of us. Therefore, I think that we need to stop thinking in terms of nationalism, and we need to think and act as citizens of one planet. Also, I strongly believe that we need more women at the table, both in disarmament, in peacekeeping and security policy, to negotiate good deals how to get rid of these nuclear weapons, because women bring critical perspectives into this topic, and they are champions of diplomacy and they drive sustainable solutions. I strongly believe that nuclear weapons should have no place in any country's defense doctrine and that their total abolition is the only way forward. Okay, that's my humble opinion. Thank you.
Thank you very much for sharing those insights. Those are very valuable, and you have provided a critical path also for more women in the diplomacy aspects. We really appreciate that, and to tell the people this is where we should go. Now we would like, before we go to the Q&A session, to ask the attendees if you can open your cameras to have a picture to remain and to capture of this great event. So we will appreciate if everyone can open your cameras. I think all of you are now allowed. to open your camera. So we will appreciate. And Shafi, please hold on your question. I've seen that you raised your hand. So please see if we can have all the participants. With their cameras. Glad to see Margaret. Noel, glad to see you. Thanks for being here today. So just a few seconds while we wait for more people in the room. Let me see.
They must be shy.
Yes, just in a minute. So please, everyone, give me your biggest smile. So at the count of 3. 1, 2, 3. I need to take one last back shot. I think that'll work. And then we will be ready to go for the Q&A. So please, at the count of 3, join me again. 1, 2, 3. Perfect. Thank you so much. So let us just get back to the Q&A session. I think we have a previous question from Christopher in the chat. I think this is for Peter. When is the warhead is finally disposed? At what happened to the place being disposed of the source? And is there any ongoing reassurance of these disposed sources?
Okay. So if we're looking at the 14-step model of the IPNW, for example, the end stage is not very well defined. There are different options. It could be that the fissile material coming from the dismantled nuclear warhead will be, let's say, declassified. It could be diluted in a sense that its isotopic composition is slightly altered to protect sensitive information, and then one could imagine that is put under some kind of safeguarded storage. On the other hand, it is, of course, some will desire to make something more irreversible to dispose of it. And one aim that is lifted up sometimes is to use the spent fuel standard. Many non-nuclear weapon states have plutonium, but it's embedded in used nuclear fuels. So in that, it's protected by the fission products that are highly radioactive. It takes time to separate it. It's technically challenging. You need a reprocessing plant, which is technologically demanding to create. So looking historically, what's been done, the US and Russia did sometime agree both to dispose of highly enriched uranium in the megaton to megawatts program by diluting it and using it in power reactors as a fuel. So eventually it's disposed of as spent nuclear fuels. They also had the plutonium management and disposal agreement between the Russian Federation and the US, where a similar tactics was proposed for plutonium to mix it into MOX fuel that has a mixture of depleted uranium and plutonium, and that was also to be used in some types of reactors. However, that agreement was discontinued before completion a few years ago. So there are options, but essentially the material could be diluted, so it's no longer as directly usable in a nuclear weapon. It could also be converted, like swords to plowshare model by using it in nuclear fuels.
Great. Thank you so much for that detailed response. We really appreciate that, and we have to be aware about the different challenges in the warheads disposal. So now we have Shafi holding here the question. Please, if you can open your mic, we will appreciate. You can ask your question to the panelist. Shafi, Musha, can you hear us? Okay. Let me just jump into Professor Mustafa Kofi's question.
Of course, I can hear you. I can hear you. I can hear
please,
you.
Can you go ahead and ask your question, please? Thank you.
Yeah, all right. I was looking forward to understand the concept of this particular virtual conference. As I've been following it with keen interest, I have noted that mostly we are looking forward to, we're talking about the nuclear treaties. Maybe we have to ban the production of nuclear weapons and the like. But to my interest, if we can look at the aspect of geopolitical influence in terms of how these particular nuclear warheads are produced, because you can see that Russia has the nuclear weapons, America has the nuclear weapons, these other countries, like the likes of France, Pakistan, they all have the nuclear weapons. They use them as to threaten the other countries who are not aligning with their maybe business or whatever agendas, of course influenced by the politics. So I wanted to bring this as a request to say, if all the countries worldwide can follow what South Africa did, South Africa destroyed their own nuclear warheads some time back. But you can see now you're talking about nuclear non-proliferation and disarmament, but of course, we are also forgetting that there are some other countries who are owning the nuclear weapons as of now. Like what happened some few months ago, we saw America went to bomb some nuclear laboratories in Iran. So that was an influence of maybe I can call it a geopolitical influence. As you can see, Israel owns nuclear weapons, around 100 of them, and then Iran is being barred from having or maybe manufacturing any of the nuclear weapons. So as far as we're dealing with these traders, I think one of the most important aspects to look at, it has to be an aspect of the influence of geopolitics in terms of the manufacturing of nuclear weapons. So I wanted to raise this as just a point. It's not necessarily as a question. Thank you so much for your attention. I submit.
Thank you, Shafi. I really appreciate we really appreciate your comments. Peter, Eva, would you like to add or comment on these geopolitical challenges from your professional perspective?
Well, allow me to say the following. First of all, the first country that I remember recently who made nuclear threats was Russia against Ukraine, like 3 years ago when the war started. On the other hand, Russia, through its Rosatom, is supplying a lot of nuclear power plants across the world. So one could hold them accountable. So please, why are you threatening a non-nuclear weapon state with nuclear weapons? And on the other hand, you want to encourage peaceful nuclear programs. Unfortunately, nobody has an influence on the disarmament aspect except those states by themselves. And yeah, another thing I would like to say, so Israel has never signed the NPT, so they are free to produce nuclear weapons, the same like Pakistan and India. And as I said, the DPRK, they did sign, but then they withdrew. So those states are out of any control. Whereas the 5 recognized states under the NPT, they should disarm, and they are not disarming. On the contrary, that's the challenge I presented. There is actually no entity to monitor this disarmament aspect. it's good that Peter and people like Peter are doing this work, how to actually then verify the disarmament process. I think that's very important once we get to the stage where those states are actually ready to disarm, but I don't see any preparedness right now. On the contrary, under the current geopolitical situation, it's really very difficult. Yeah, and there shouldn't be any attacks of nuclear facilities, whether it's in Chernobyl or Zaporizhia or Natanz or Fordo or wherever, or Esfahan. There shouldn't be any attacks of nuclear facilities nowhere by nobody. So not just by Israel and the US, but also by Russia, for example. That's my humble opinion.
Thank you. Peter, would you like to comment?
Yeah, I mean, I essentially agree that, I mean, of course, there needs to be a political pressure on states that have nuclear weapons to gradually abandon them. Right now, it seems to be rather a pressure to get more of them. So we are currently failing in that. If we want to be optimist, I mean, looking back in history, there has been occasions where there was peace and prosperity was seeming to win over the Cold War at some point, and at that point, many disarmament steps were taken. So times like this will inevitably change to times that are more suitable for disarmament. And I think that the main, I mean, I think maybe one can have sanctions, positive or negative, to put pressure on states. You know, maybe one can have that, and that may or may not be effective, I think. But the main driver toward disarmament has to be the understanding of world leaders that the nuclear weapons are dangerous, and that major conflict involving nuclear weapons will be very harmful to everyone. And from that understanding, I mean, there should come a motivation to disarm of them together. And it has been shown that this will happen in beneficial circumstances. Like we had the megaton to megawatts program where one tried to really achieve steps, and you have the bilateral disarmament agreements as well that we had in place. Now they're falling one by one. So what I want to say is that if we can just have a credible peace, the nuclear weapons have no function. And then we just need to have the technical tools and the verification tools ready so that we don't miss the opportunity. Right now, yes, it doesn't look promising, but also because people are more afraid now of nuclear, it can also change fast, I think. That's I work under the belief that times may change fast in favor of disarmament, and then we must be ready. So that's my 2 cents on this.
Thank you so much for that insight. And with the current challenges, I mean, we cannot predict everything, but everything can change rapidly. Public acceptance and different misconceptions. I'd like to go through Professor Mustafa Kofi's question. He's asking, any new solutions such as blockchain implementation for overcoming adversaries exploding allow difference between 2 or 3% between each nuclear material accounting areas, and when converting measurements from bulk to counting. Would you like to comment in the implementation of blockchain technologies and so on in the nuclear accounting material place?
Well, allow me to say something on this. I know that the IAEA is looking at introducing blockchain technology for IAEA safeguards in cooperation with some member states. And I know that some member states are also looking at using blockchain for following transactions of nuclear materials by sending nuclear material from one state to the other. I'm not aware about the application of, in the case of bulk handling material, it would be a little bit difficult, I think, but it's definitely there are ways, there are attempts to introduce blockchain technology. It's a long process. The IAEA has their safeguard system, a huge database going back to the 1960s with all the inspection results and nuclear material accounting reports, etc. So there would be, one needs to see how one can move that into a new system using blockchain technologies, but there are efforts in course for that, as far as I'm aware.
Thank you so much for your insights, Mrs. Eva. It's still a long way to implement also blockchain and verify the data. How is implementation of these robust databases? Peter, would you like to add something related to blockchain practices and implementation?
I don't think I have any key insights on that point, but if blockchains can be implemented in safeguards by IAEA, I think that I mean, it's probably going to be transferable to some extent to the nuclear disarmament regime. So I think we'll follow in that case.
Definitely. Thank you so much. Let's get to Adenia's question to close this Q&A session. Please, Adenias, if you can open your mic, we'll appreciate that. Adenia, can you hear us?
Thank you so much. I can hear you.
Yes.
My question is, you know, just my thought, and which is human nature. It's very difficult to be able to pull all these nationalities, specific individuals, the leaders and everybody else, to a particular point whereby that the whole world, like we are discussing, that the world does not need nuclear weapons. Like in the case of Ukraine and the other Baltic nations and the ones that were the former Soviet Union, they were convinced to surrender their nuclear warheads, and they were convinced that they will not be attacked, or if they were attacked, they will another nuclear state like the USA was like a guaranteeing their safety, to be able to help them to retaliate back. And now we see we are in a position whereby these particular nations are feeling betrayed because they surrendered the nuclear warheads to the current Russia now. And how do you go about convincing the other states, like in that region, we are well aware that they are now running to join the NATO, North Atlantic Treaty Organization, because they fear that Russia can actually use nuclear weapons against them. And now they are even in a position of reconsidering, thinking that they made a mistake. So I think in my comment, it will be so difficult to be able to convince the other nations that are getting into nuclear to be able to get into those type of treaties. Like, for example, the treaty that you just shared, I don't know, it was called TPW, something like that. I realize people like the US, Russia, I mean, you said in Europe, it's only Austria and another nation you mentioned. I actually checked. Then you check that the majority of nations like France that have a stockpile of nuclear weapons, they're not even part of that treaty, meaning there is no goodwill, meaning the other nations that are even surrounding them will not even be willing to be able to participate in that type of technology. I mean that type of treaty to be able to hinder this escalation of nuclear warfare and that type of thing. And then my question would be, could we find ourselves in a situation whereby even the enrichment to weapon grade fissile material will happen a little bit faster? Like in this case, people are trying to look at being able to do enrichment using lesser technology. So we know what has been hindering them is the aspect of time. And what if you get into a position whereby like in 2-3 years, you already have 90% enriched uranium because technology is already progressing? We used to think such a type of discussion like, video calls and whatever was so far away. And yet nowadays, technology is moving so fast. What if we get into a position whereby people like, like Iran we are talking about, the only thing that has been hindering them is time. they get a technology and they pour money into it, this like laser separation, and within like 2 years of having that technology, IAEA will not even be able to respond. And is there any consequence for not, keeping up to the agreements in the treaties? Does IAEA even control the fissile market, the fissile material market, like uranium market? Like, can they hinder people like Ukraine, people like Iran and the other nations that are trying to attain this fissile material for nuclear weapons? Are they able to hinder these companies? Like, don't export uranium to Iran? Because if there is no consequence, and if you don't have control for market, then everything will always go in the opposite direction. Mankind is always bent on trying to do something that is against the law. That's like the nature of mankind. Thank you so much.
A very
Thank you.
comprehensive and difficult question, Adenia.
Yes.
As I mentioned during my presentation, once states sign up to the NPT, they are obliged to place all nuclear material on their territory and all facilities under IAEA safeguards. So we have seen that one of the success stories of IAEA safeguards at the NPT have been that we have just maintained those 4 states outside the NPT, and we have not, Iraq tried to proliferate in the 1990s. The program was discovered, which led to a strengthened non-proliferation regime, IAEA implementation techniques, etc. So those states are obliged, and the non-nuclear weapon states are also obliged to report any exports to non-nuclear weapon states. So there is some type of monitoring. But of course, there may still be entities in a state that may do things that they are not supposed to do. But the states are still obliged under those treaties. And if that comes to the light, there will be problems. For example, if the IAEA finds non-compliance by a certain state, it first reports it to the Board of Governors. And if the Board of Governors takes a corresponding resolution, this goes further to the UN Security Council, as happened in the case of Iran in the early 2000s, when the undeclared enrichment and heavy water program were discovered. So there are provisions for that, but of course you can never exclude how should I say, activities also on the level of non-state actors to be happening. But I don't think this would be some companies, because the companies should be all controlled. It would be rather at some nefarious persons in a state that would try to do something like that. And enrichment is, as Peter has mentioned, is a very difficult technology. By lasers, it's even more difficult, and you always need the material that you want to enrich, which should be under IAEA safeguards and under IAEA monitoring. So, yeah, that's what I would like to say to this question.
Thank you. Thank you very much for that comprehensive answer. And still, there are mechanisms that avoid to proliferate or to take fissile material into a different stage. Peter, would you like to comment on this question?
Well, let's acknowledge that technology is improving, and it may gradually become new methods available to the non-compliant state and so on, and that brings challenges. On the other hand, you also get new tools to perform the verification because of technological development. I will say that the state that signed and ratified the NPT does that also because they want their neighboring states in their environment to do the same thing. It's a mutual agreement with all the members of the NPT that we don't achieve nuclear weapons. And if you're thinking about cheating on that, you can try, but you will be exposed to a risk of detection. So that should deter you from doing that. There is at least a dangerous activity for yourself to be non-compliant with the obligations that you have agreed to. In particular, of course, if the NPT is also combined with the additional protocol that you heard about earlier, so it's difficult to hide some activities altogether. You will need your uranium mines to get the raw material. You need to refine it with enrichment or a nuclear reactor. All these things are substantial financial costs in your budget. It takes qualified personnel. It takes the physical space, and it can be detected by curious neighbors, so to say, and they can alert the IAEA. So you don't get around that. Yes, you can try to cheat. Anyone can try to cheat if they have the motivation, but there will be a substantial risk of detection, and that does deter from pursuing that. So I have big faith in the IAEA when they make a statement that the state is using nuclear technology peacefully. But I know that some people express doubt sometimes. But I think we can have faith in IAEA that has been trusted with this mandate, that they do the job well.
Thank you, Peter. Let's continue also to enhance different practices for IAEA, Uppsala University, and different organizations that are promoting the disarmament practices and techniques around the world. With this, I would like to conclude my participation and thank the speakers for your wonderful presentations and the knowledge you had transferred to us today. And please, Lancina, I would like to hand over to you for closing remarks. Thank you.
Thank you.
I think you're muted, Lancina.
Thank you so much. Thank you so much. It was very, very wonderful. I forget to meet. Okay, I want to extend my sincere thanks to our exceptional speaker, our engaged participants, our dedicated organization team for a truly insightful discussion on the urgent yet complex topic of nuclear disarmament and the essential role of verification. We have heard today about the immense danger this weapon poses, a constant existential threat to humanity and future penetration. In future generation, we are exploring from scientific cooperation to build a robust international institution that can help us move closer to a world free of disarm. Caretaker of our journey for our verification is not negotiable. As in light there can be no credible disarmament without systematic, effective verification requiring independent, robust protocol. Bridging divides, we must build an area of consensus and work constructively to overcome difference recognition and parallel progress in disarmament. Proliferation is crucial. Collaboration is key. One second, excuse me. Collaboration is key. The success of past efforts like the scientific expert work on the CTPT show that global scientific and political cooperation for treaty even in challenging times. The path to total universal and irreversible disarmament is long, but our discussion today proves it is path we must work together with fresh idea and shared commitment to international security. Let this webinar not be the end, but a catalyst for continued dialogue, action, and engagement. Let's carry this insight forward, fostering the collaboration to make verified nuclear disarmament a reality. Thank you again for your invaluable contribution. let's keep the conversation going. Stay safe and goodbye. Thank you so much.
Thank you very much. We wish you to have a very good rest of your day, and we really appreciate all your engagement, cooperation, and support. This is the end of today's program. Thank you.
Thank you. Thank you so much. Bye-bye.
Bye-bye.
Bye-bye.